commenting on Vladlen Koltun's presentation at ETH Zurich he gave a month ago. And he was talking about embodied intelligence and the embodied approach, bottom-up, versus the top-down approach from cognitive symbolic logic down to the embodied intelligence, and how his opinion about how to actually surface intelligence has changed from the idea that you need embodied intelligence to actually develop intelligence, because that's how nature developed intelligence, and how the recent success with, call them cognitive models, that those are models that the frontier labs came up with, GPT, Grok, Claude, and things like that, Kimi, where you don't have embodied intelligence, but you have enough semantic understanding of the world that it looks like you could also get to intelligence through that route. So he's giving this talk. He's talking about the Moravec paradox: the hard things are easy, the easy things are hard, and how it looks like maybe we should start with the easy things and then go to the hard things. That's kind of his main message. So he's a little bit more humble than maybe others in trying to assess the change in the landscape. So this talk is more like, okay, look, something has changed here. We can potentially develop reasoning and intelligence in space through the top-down approach. That's his main message. Our take on this is that that's probably not going to work. Now, it's difficult to make predictions in this field, but it's just intuitively hard to believe that you can learn jiu-jitsu just from watching videos. You can initialize, you can pre-train a robot to do that, but then the robot actually has to act in space, do things, and then maybe feed back into a model, into a simulation engine, learn, and then go back to the real world. So you need interaction with the real world to learn how to act with the real world, and that is because the cognitive knowledge that we have of the real world is a very limited level of knowledge. Nobody can explain to you how a 20-foot wave is surfed, or a steep rock is climbed, or a moving jiu-jitsu actually works. You can talk as much as you want, but you actually have to do it to understand. You have to feel it to understand. And other things like sex, of course, also don't work like that. Now, my point being that I appreciate Vladlen. I mean, he's one of my key figures to go to, even though he's working at Apple now, which is a bit, I would say, it's like a soccer player that plays in Turkey or somewhere like that. Like you're a talented player. Why don't you play in a top league, in the top team? And AI and Apple aren't exactly a good match. Nevertheless, I think he's a very important figure in AI, because he's done the drone race. He's done the sort of the AlphaGo. He's done the AlphaGo moment. He's created the AlphaGo moment for robots when he won a drone race together with Scaramucci from University of Zurich, when they beat human racers. So I think, therefore, he has done something that warrants him being listened to. And he works with Jitendra Malik and people like that. So clearly, he's in the top league. So our view of this, and we want to use his talk as an inspiration to reiterate our view, is that yes, we can of course use all the tools available to speed up intelligence. So, for example, we can use definitely the semantic understanding of cognitive models. Turn left over there. Don't drop me next to this tree, or drop me over there. Things like that. Let's say using Grok in a Tesla car is definitely very useful. However, with the way we see the robot learning pipeline as we speak today, is that we want to have an interaction between the cognitive models and the real world. And we want to pre-train from video to have a basic understanding of moving in space. Moving in space is a different type of intelligence than understanding language or code. And moving in space requires understanding that you're in front of a tree, that there's something behind the tree, that you don't want to hit the tree, things along those lines. We also believe that Tesla has solved a lot of these problems with FSD natively end-to-end, meaning they haven't explicitly solved this by representing the learning process in a way so the car can learn, where it is in space. It's just learned through enormous amounts of scale. So they've applied the bitter lesson here. Now, that doesn't mean that that is the only way they should be working. And I think, having listened to Ashok now several times this year, it's clear that they're trying to improve the models with the semantic knowledge of let's say, Grok, with using, different architectures like transformer architecture to improve, spatial reasoning. Spatial reasoning as a concept, I think, is incredibly important. So chain of thought or chain of trace of thought, or whatever you want to call it, like the analogy of chain of thought in large language models would be reasoning in space. That concept is very important. AlphaMayo, the NVIDIA self-driving model, is using it also. So clearly that's something that's very interesting. I think also Ashok spoke about the debugging of the model by using reasoning modules that aren't explicitly exposed to the end user, but they are implicitly used during training, so you can debug. So let's say if you make a mistake, you can kind of follow back and see why the model made the mistake, things like that. And it looks like also that you want to be able to train the robot in a way that it can generate its own trajectory and therefore learn how to deal with out of distribution data by bringing it in distribution, or by bringing itself back to a state where it can then try to iterate around possible solution when it faces an out of distribution situation. So if a Tesla FSD sees a tree on the road and an elephant on top of the tree or something like that, it can start reasoning, okay, what should I do now? Now, I think there's two things I want to say here. This is a big topic, so I could talk for hours, but there's two things. First, I want to define exactly what we mean with spatial reasoning, because it's important to understand the trajectory of this idea. And then the second thing is, again, we want to elaborate on the robot learning pipeline, which we believe is a combination of in simulation training and then also real world interaction. And then there's a sort of a feedback loop. So let's start with the first thing, which is, okay, what do we actually mean with spatial reasoning? So if a robot understands that it has to go, let's say, to open a door, that it has to go towards the door and open the door, and it understands that the opening the door means going to the door. It also understands that on the way to the door, it shouldn't, walk over somebody, things like that. I would say that is not spatial reasoning. That is common sense. That is the kind of stuff that large language models can give to the robot. Also, importantly, what something like a Grok can give to the robot is, of course, the actual management of the process, or the management of the workflow, which is what we're seeing right now with Claude Code and Codex and Grok Heavy and things like that, where you have workflow management, software development, or other workflows, Coworker, like Claude Coworker, where you manage workflows. So, for example, we could see Grok managing a robotaxi network, but that's not spatial reasoning. Spatial reasoning is literally, you're on the highway and you understand that taking over a car involves you now turning to another lane, that there is something behind you, something in front of you. That kind of spatial reasoning, which is not explicitly, that's, you can obviously mimic that with something like a large language model, but I don't think that's enough. I think that's where we really have truly native spatial reasoning that Tesla has developed with FSD. It's the only place that we know where embodied AI has real spatial reasoning, and it's been trained end to end without representation. We spoke with Ranjay Krishna about this. He's trying to find representations that help move forward to spatial reasoning. Even he admitted that if you have enough data, you can actually apply the bitter lesson here. But it doesn't hurt to also think about representations, architectures that enhance or speed up the spatial reasoning. But fundamentally, spatial reasoning is about understanding your situation in space relative to other objects. And it's not, it doesn't have to be now, you know, Vladlen talks about things like understanding, okay, if I'm left and this is over there, then what angle is the other thing? Like that to me, that's, I mean, it is, of course, geometric reasoning, and it kind of, you know, it's Euclidean logic, and those things are, I would say, on the crossroads of spatial reasoning and cognitive reasoning. But real spatial reasoning is when I surf a wave, when I apply an armbar in jiu-jitsu, when I you know, ski down a slope or climb a rock. That's spatial reasoning. I don't think about my relationship to the rock. I don't think about my relationship to the wave, the forces, none of that. I just do it, and I intuitively know how to do it. That kind of spatial reasoning, I think, is possible with robots, but they have to be trained in interaction with the real world. Now, the second point is the robot learning pipeline, and we've spoken about this before. I just want to reiterate this. So we have, you know, a pre-training phase that we see that can be done. Training for, like, what you need in pre-training is just a massive amount of data that gives you a sort of basic understanding of moving around in space without specific skill or anything like that. And that, we believe, can be done from video. The next phase then would be to do the mid-training. Here we spoke about, let's say, the work at CMU that we just spoke about just recently. Links in the show note. I think Professor Kumar, like, okay, how can we mid-train more effectively? For example, by correcting actions instead of teaching the robot how to do things. Now, these are, you know, specific reinforcement learning type methods to increase the speed of exploration and also increase the performance of learning itself. So getting faster to better decisions, basically cutting off the action space very quickly, telling the robot, look, don't do this, stop, think about again what you're on the wrong path. So something like that. But in principle, mid-training involves enhancing the ability of the robot now to execute against actual skills. What we then see is deploying the robots in the real world, and that's very important because the robot is a data collection engine as much as it is a useful working tool. In other words, because the robot acts in real space, we actually do have what FSD has already, and that's a data set of images and in 4D, so videos and actuators, and they're fully synchronized. That's what's important, because that's, you know, and now, in order to learn from that data set, in order to learn anything, you always have to have counterfactuals. You have to have counterfactuals because that's how you learn, right? If you're, you know, a KUKA robot is deterministic, it doesn't learn anything. It does always the same thing. It only, you can learn maybe if it does something wrong. So there was a counterfactual there, should have done this, but it did that. So we can fix that problem. But fundamentally, of course, if you want to have a continuous learning process, continuous improvement, continuous learning, you need counterfactuals. So we have the pre-training, we have the mid-training, and now we deploy the robot in, let's say, you know, working in the factory, cleaning the factory, or you know, screwing a screw or hammering a nail or things like that. What we need is, of course, counterfactual. So the robot does something, and then there's a model that runs parallel, maybe generates its own trajectories and compares what the robot does with its own trajectories. And then when there are discrepancies, then learns from those discrepancies what the right thing would be. The right thing would be, you know, you can induce the right action by offering rewards through RL against the goal, for example. We could go even further, learning from experience. So we could actually even not even give rewards, but just look at the behavior. For example, if the robot is supposed to clean the apartment and it doesn't get deployed again, maybe there's 5 robots and there's, you know, the one that does the best job keeps getting deployed, so the other robots just copy the weights of that robot. So I don't know what that exactly means. we're talking here about Richard Sutton's ideas, and I don't want to go there now. My point is, we need a data flywheel here between the in-sim cognitive learning phase, which is in pre-training and in simulation and mid-training, but we also need real data, and then we need to feed that back. So the in-the-loop training is very important to us. So to summarize, I think Vladlen's presentation is very inspiring as usual. I think he opens up a door that is basically what he's saying is, look, we embodied people shouldn't just be focused on embodiment, and cognitive people shouldn't just be focused on cognitive. I think there's a good mix. I don't know how far he wants to go there. Now, our belief here at Orange Capital Partners is that it will happen through scale. It will happen through robots, humanoid robots that actually have a very low morphology gap with humans, because that is the robot that we can learn from. There is actually an embodied AI that does a lot of work that we care about, that is a human, and we can learn from that human by learning from video, and then through mid-training, and then in-the-loop training, improve the skills of the robots and get ourselves to a world of embodied intelligence that is very useful for us. Whether that is artificial general intelligence or not is actually irrelevant. We agree with Koltun here that it's a stupid problem to solve artificial general intelligence, because there's no such thing. There is only useful intelligence. There is commercially useful intelligence. There is intelligence that people value and pay for, and that is the kind of intelligence that we're interested in. Thank you.